Hi everyone, and welcome to my continuation of the video on rational functions and their graphs. In the previous video, part 1 of this video, we talked about the definition of a rational function. It's a function in the form of a fraction where that fraction is made up of a polynomial over a polynomial. We did a couple problems involving the end behavior, the behavior around asymptotes, the behavior around points. This was number 1. Number 2, we did about 4 problems on finding vertical asymptotes, A, B, C, and D. These are all covered in the previous video, part 1. We did, I think, about 6 of these horizontal asymptotes, A, B, C, D, E, and F, I believe. Yep, F. And this is where we left off, graphing a function. So this is putting everything that we've done previously in part 1 of this video, along with 4 or 5, maybe 6 items from previous topics, previous videos. So this is not by any means the order you have to do these steps, and sometimes not every one of these even applies. But if you want to take one step-by-step method that works for every problem in which you have to graph a rational function, this one works pretty good. Okay, so step 1, symmetry. Does the graph have symmetry? This is the one step out of the 7 which I would say is optional. Knowing if a graph is symmetric, sometimes it makes it a little bit easier when you're down here in step 7 when you're actually graphing. But we could do without it if we need to, but it's here, so we're going to do step 1, which is symmetry. Step 2 and step 3 are the intercepts, the x and y intercepts. That's something we've covered in multiple previous videos, a lot of different contexts and types of problems where we're finding x and y intercepts. Then we find the asymptotes, vertical and horizontal asymptotes. So that is basically that's the new stuff right there. That's in terms of this section, this topic, rational functions. That step 4 and 5, that's the only part of this process or this graphing problem that's new as of now. And then step 6, just to make sure our graph is right, we'll plot at least one point between x-intercepts and asymptotes, and just to make sure our graph is looking good. So it's actually 6 steps, and then step 7 is just do it all, right? To take all of that information from the first 6 steps and then make your graph. So let's do a couple of these. Let's see how this shakes out. So the first one, we've got graph the rational function f of x equals 3x minus 3 divided by x minus 2. Okay, so let's see if we could graph this guy. I mean, we could definitely graph it using technology. We could, plug this into the graphing calculator or type it into Desmos. But what we want to do here is make sure we could do this by hand. And you're actually going to do this again in Calculus 1. Most likely, we go through a process of graphing. And what we do in Calculus 1 is everything we're doing here, we're going to redo it again in Calc 1 and add a little bit more detail. Something involving the maximums and minimums and the turning points, which are things we talked about earlier when we talked about polynomials. All right, so let's talk about symmetry first. So to test any function, this is not just for rational functions, but to test any function for symmetry, this is what you do. Replace x with negative x. And one of 3 things is going to happen. That's going to be equal to the original function, or that's going to be equal to the opposite of the original function. That means every single thing changes sign. Everything positive becomes negative. Everything negative becomes positive. That's what negative f of x means. Or the most likely thing is neither. Right? One of these three things is going to happen. Most functions are not symmetric. Most functions are not. If you plug in negative x to your function and you get the original function back, that means your function is even. If you plug in negative x for x and you get back the opposite of your original function, then the function is odd. And if you get back something different, it's neither even nor odd. Okay? So even means y-axis symmetry, and odd means origin symmetry. So let's see what happens here. F of negative x is equal to, well, replace every x with a negative x. So instead of 3 times x minus 3, it's 3 times negative x minus 3. And then on the bottom, instead of x minus 2, it's negative x minus 2. Okay, so that's negative 3x minus 3 on top, negative x minus 2 on the bottom. That's not the function we started with. That's not the original f of x. So it's not even. That is not the negative of the original function because only some of the signs changed. The 3x became negative, but the minus 3 on top stayed minus 3. So that's not odd. So there's no symmetry. Well, at least there's no origin symmetry and no y-axis symmetry. Okay, let's find our intercepts. To find the y-intercept of a function, any function, not just a rational function, but any function, this is what you do. F of 0. That's how you find your y-intercept. Because when you do f of 0, you're basically completing the point. 0, comma, something. Right? That's what we're doing when we do f of 0. When x is 0, the point is on the y-axis. So f of 0, that would be 3. Instead of 3 times x, 3 times 0 minus 3. And on the bottom, instead of x minus 2, we've got 0 minus 2. Okay, that's negative 3 over negative 2. The negatives cancel, and we get 3 over 2. Okay, so that means the point 0, comma, 3 over 2 is on the graph. As soon as we find some piece of information, we should go ahead and, oh, I said positive 3 over 2. Let's get rid of that. And so we have a y-intercept. Okay, now let's move on to the x-intercept. For any function, not just rational, but for any function, we solve the equation f of x is equal to 0. Right, for the y-intercept, you plug in 0 for x. For the x-intercept, you plug in 0 for y. So we're solving the equation 3x minus 3 over x minus 2 is equal to 0. And a fraction is equal to 0 when the numerator is 0. Like if we multiply both sides by x minus 2, it'll cancel off the x minus 2. So we only need to solve the top of the fraction is equal to 0. Could add 3 to both sides. So that's 3x is equal to 3. We can divide both sides by 3. So we'll get x is equal to 1. X is equal to 1. So that's a point on the graph. 1, comma, 0. That's where the graph crosses the x-axis. Now what we're doing here, these are now restrictions on the graph. This is important because we want to make sure we're drawing the graph accurately. So what we have right now are two green dots, 2 points. This one right here, that's the only place the graph is allowed to cross the y-axis. And this guy right here, this is the only place the graph is allowed to cross the x-axis. We have found the x-intercept, we found the y-intercept, so there's no other place the graph could cross either axis. Okay. I can't remember which was first, vertical or horizontal, but let's just do vertical asymptotes first. So the first question is, can we simplify this fraction? And there's not much we could do. I mean, we could factor out a 3 on top, but that's not going to cancel anything on the bottom. So this fraction is as reduced as it's going to get. And so for the vertical asymptote, we have our fraction in reduced form. We want to know when is the bottom, when is the denominator equal to 0. And if we add 2 to both sides, we get x is equal to 2. So that means there is a vertical asymptote that passes through the x-axis at 2. The function is undefined here. The graph cannot cross this dotted line. This is a dotted line that says the graph is undefined here. Let's move on to horizontal asymptotes. So we'll call this 5. Let me just rewrite the function. F of x is 3x minus 3 divided by x minus 2. The degree of the top is 1, x to the first power. The degree of the bottom is also 1. So the numerator, the denominator, the top, and the bottom have the same degree. So our horizontal asymptote, let me be more specific up here. For the vertical, the line x equals 2. For our horizontal asymptote, it will be the line y equals 3. We look at the leading coefficient on top, the leading coefficient on the bottom. On the bottom, we have x minus 2, right? So when you see x by itself, there's really a 1 in front. So that's 1x. So leading coefficients would be 3 on top, 1 on the bottom. 3 over 1 is 3. So that means we've got a horizontal asymptote. Remember, this is a label of the end behavior of the graph. The graph is going to level off at positive 3 in both directions. Okay, so what we could do here is let's plug in a point or a number or two, generate 1 or 2 points. We have nothing on the right of that vertical asymptote, nothing to the right of 2. So let's see what happens when we plug 3 into our function. What is f of 3? I'll replace the x with the number 3. So instead of 3x minus 3, it's 3 times 3 minus 3, a lot of 3's. On the bottom, 3 minus 2. So that's 9 minus 3 is 6 on top, 1 on the bottom. So when we plugged in 3 for the x, we ended up with 6 for the y. So that's another point on the graph. When x is 3, y is 6. So it's going to be up here somewhere. It's a little bit off the graph because this grid only goes up to 5, but I think that graph is, well, we know it goes up and down forever. It goes up to positive infinity and down to negative infinity. All right, and let's just plug one more point in. I'll use a different color to keep everything straight. Let's say f of, I don't know, something something to the left of 0. Let's plug in, I don't know, negative 2. Replace x with negative 2. So that is 3 times negative 2 minus 3 on top. Negative 2 minus 2 on the bottom. So on top we get negative 9. On the bottom we get negative 4. And that looks like about 2.25. Okay, so there's another point. When x is negative 2, the y value is 2.25 or 2 1/4, however you want to describe it using decimals or fractions. So the more points you have, the more likely you are to make an accurate graph. So when x is 2, here's 2 on the x-axis. I'm going to go up to 2.25 on the y-axis. So about right there. Okay, so these dotted lines, these are labels on the graph. The vertical line is the vertical asymptote. The horizontal line is the horizontal asymptote. The graph has to approach these lines. For the horizontal asymptote, either from above or from below. For the vertical asymptote, either from the left or the right. So when we draw this graph, it's going to look something like... So that's going to be getting closer and closer. Let me draw it even a little bit closer. It's going to be getting closer and closer to that horizontal asymptote. It's got to hit that point. And it's got to hit that point. Then it's got to hit that point. No straight line segments. No corners. This is all smooth, continuous curve. And then it's going to come down here and approach the vertical asymptote in this direction. Then we've got this point up here, this guy. And there's got to be some graph to the right of that vertical asymptote. And from that point, the graph's going to come down and approach the horizontal asymptote. It's going to go up and approach the vertical asymptote. This line continues, goes to infinity in all directions. Okay, I hope that was okay. I squeezed a lot onto the screen because I wanted to have all the work there all in one place all at once. All right, so this is the process. This is graphing a rational function, and this is there's a lot of overlap between this and the process we use for graphing other types of functions. We just finished graphing polynomials. It's almost the same process. Almost the same process. The difference being sometimes rational functions have asymptotes. All right, let's do one more. We can go through this one a little bit quicker because we've done a lot of explaining on this example. So last problem for the video, number 6. Same problem, different function. So in this case, we've got the function f of x equals x minus 3 divided by x squared plus 4. X minus 3 divided by x squared plus 4. So let's go through the same steps. Number 1, symmetry. F of negative x. So that'll be negative x minus 3 over negative x squared plus 4. Replace those two x's with negative x's. On top, we get negative x minus 3. On the bottom, when you take negative x and square it, negative x times itself is positive x squared plus 4. So let me write our results in green. Not even. Right, we don't get our original function back, and we don't get the negative of the original function. Not every sign had changed. The x on top became negative, but the minus 3 stayed minus 3, so it's not odd. So just like the last problem, it's neither even nor odd. Again, most functions are not symmetric. Most functions are not symmetric. Okay, what is the y-intercept? What is the y-intercept? So plug in 0 for x. So we are doing this. Here's half of the point. What is the other part? Well, what is the other half of that point? So when x is 0, we get 0 minus 3 on top. And we get 0 squared plus 4 on the bottom. So that looks like negative 3/4. So when x is 0, y is negative 3/4. And let's go ahead and put that point on the graph. Let's plot that one point right there. Negative 3/4 on the y-axis. Okay, let's get our x-intercept or intercepts. There could be more than one. Sometimes in this problem, I think we're only going to get one. So we set the function equal to 0, which is, we only need to set the top equal to 0. So that's x minus 3 is equal to 0. Add 3 to both sides. And we get, what do we get? X equals 3. So when y is 0, the x value is 3. For the y-intercept, plug in 0 for x. For the x-intercept, plug in 0 for y. Okay, so now we got 2 points plotted. Next, I think we did vertical first and then horizontal, so let's do the 2 asymptotes. Let's start with vertical asymptotes. I'll just say VA for vertical asymptote. If we look at this function, f of x equals x minus 3 divided by x squared plus 4. Well, that doesn't simplify anymore because the top doesn't factor. That's just x minus 3. And actually the bottom doesn't factor either. Be careful. Don't, I've seen this before. X squared plus 4 equals x plus 2 times x plus 2. This is not true. This is absolutely false. If you multiply out the right-hand side, you don't get x squared plus 4. So x squared plus 4 does not factor. Does not factor. So when is the bottom equal to 0? Well, never. X squared can't be negative. So if you take something that can't be negative and add 4, it's definitely not going to be negative. But If we actually go through the motions and try to solve for x, we quickly see x squared is equal to -4. Now you try to take the square root of both sides, and you're taking the square root of a negative number, so you get plus or minus 2i. So the result here is there are no vertical asymptotes. So let's move on to horizontal asymptotes. We've got x minus 3 on top. We've got x squared plus 4 on the bottom. This is the degree is 1 on the top. The degree on the bottom is 2. X to the first power on top, x to the second power on the bottom. When the degree of the bottom is a larger number, when the degree is higher on the bottom, the line y equals 0 is the horizontal asymptote. I'm going to say HA, horizontal asymptote. Okay, so, what does that mean? Well, now we've got a horizontal dotted line. That's our horizontal asymptote on the x-axis, but we also have a point. So this looks like we have a point on an asymptote. That's okay, as long as it's horizontal, right? You can never have a point on a vertical asymptote. A vertical asymptote is a label saying this is where the graph is undefined. A vertical asymptote is a label that says this is where the graph is undefined. A horizontal asymptote is also a label. It's a label of the end behavior. It's saying this is what the graph does. This is what the function values do as the x values get really, really big. Horizontal asymptote is a label of end behavior, really big in the positive direction or really big in the negative direction. So you can have a graph hit or cross a horizontal asymptote. All that means is the graph is going to, from that point, is going to turn around and come back to the asymptote. Or it could from the bottom, one or the other. It's going to either go above the line or below the line, but it's going to come back closer to that dotted line. We got to figure out what's happening though. Okay, so now let's plug in a couple points just to make sure our graph is in the right place, because right now all we have are 2 points and 1 dotted line. That's actually enough. That's all we need. But just to be sure, let's generate a couple more points. So let's say, what happens when x is equal to, I don't know, -2. When x is -2. Well, that's -2 minus 3. I'm just replacing x with a -2 over -2 squared plus 4. I hope I'm not writing too small, but I'm running really low on room. So that's the point, x -2. And for the y value, on top, -2 minus 3 is -5. And on the bottom, -2 squared is 4. 4 plus 4 is 8, so -5 over 8. So if you convert that to a decimal, -0.625, or keep it -5/8, either way, it's negative, and it's above -3/4, so it's above the y-intercept, so it's up here somewhere. All right, let's try positive 1, f of 1. So on top we get 1 minus 3. On the bottom we get 1 squared plus 4. So when x is equal to 1, the y value, 1 minus 3, so that's negative 2 on top. 1 plus 4 is 5, so negative 2/5. When x is 1, we get negative 2/5. So somewhere, maybe about right there. Wouldn't hurt to do just one more point. Let me use a different color here. So let's say f of, I don't know, f of 5. So you get 5 minus 3 on top. 5 squared plus 4 on the bottom. So when x is positive 5, the y value, 5 minus 3 is 2. 5 squared is 25 plus 4 is 29. 2 over 29, that's really small. That's really close to 0. So the point is, it's positive. That's what's important. It's above the x-axis. So I think this is a good amount of information. The horizontal asymptote is the end behavior. So as the graph goes to the left, it's got two things we know. One, it has to get closer to that dotted line. Two, it cannot cross the x-axis. Right here, that's the only x-intercept. X equals 3. So the graph cannot cross the x-axis anywhere else other than x equals 3. So it's got to go from this point to this point to this point to this point, cross the x-axis to this point, and then it's got to come back and follow that dotted line to the right. These are all things you could verify very quickly, at least the final graph, very quickly by just typing this function into Desmos. But Desmos is only going to give you step 7. It's not going to give you step 1 through 6. So if you have to show your work and if you're getting graded on, each of the steps involved, technology is a good option to check your work. But if you need to show your work, this is a good, efficient, and effective 7-step process. Why do I have 1 through 6? Oh yeah, step 7 is the graph. Yeah, sorry. Step 7 is over here. Put everything together. That's step 7. Okay. I hope this was helpful. That's it for this video.